Okay, so we are done with the brute force design technique and decrease and conquer design technique. Right? Today we will look at divide and conquer. And divide and conquer is a powerful design technique, as you might have already known. This is one of the techniques that was used by Britishers to conquer and capture lands, right, across the world. Okay, so this is a very powerful technique. So what is the idea here? You split a problem into subproblems, multiple subproblems, often greater than or equal to 2, and then you recursively solve them and combine the solutions, right? That's the rough idea. Okay, so we are going to cover in probably 3 lectures, right? So several problems. One is on array sum, array estimation, prefix sum, and we will look at recurrences. This is not a problem, but this is an idea. Recurrences are the recursive relationships for the complexities of divide and conquer algorithms. And we want to know how to solve these recurrences. So if we know this, we can write all the complexities in recurrences and probably use a formula or something like that, right? A theorem result to attack it. Okay, we will cover recurrences, and then in the second session, probably we will learn merge sort and quick sort, right? In the second lecture, merge sort and quick sort, these are extremely famous, popular sorting algorithms. And probably we will not have time to cover bitonic sort or bitonic sort. In the third lecture, we will cover integer multiplication algorithm, right? Divide and conquer integer multiplication algorithm called Karatsuba's integer multiplication algorithm, and a divide and conquer matrix multiplication algorithm by Strassen. There are many divide and conquer algorithms, but we will learn the algorithm discovered by Strassen. Okay, we will not have time to cover polynomial multiplication and probably coin toss also. Well, right? Let's see. So in 3 lectures, we want to cover as much information as possible, the lot of problems, and you know the intuition behind them, takeaway, design, complexities, everything. Okay, so that's our goal. Let's start. So as I said, divide and conquer is a design technique, right? It's like a tool in your toolbox. You can keep using this tool for a lot of problems, right? So you want to understand divide and conquer. So what is the core idea here? You have a problem, right? The problem size can be n, or it can be m comma n. It can be a multi-parameter problem, right? Multi-parameter problem. Okay, so for simplicity, let's assume it is n. And then you split this problem into multiple subproblems. 2 or more number of subproblems. Okay, why 2 or more? What if it is 1? If it is 1, we know, we have already seen that technique before. We called it decrease and conquer, right? Decrease and conquer, and not divide and conquer. Okay, often what happens is many textbooks combine this decrease and conquer and divide and conquer. But as I initially said, Anani Levitin has created this great, very beautiful taxonomy, and he divides these kinds of techniques into decrease and conquer and divide and conquer. Decrease and conquer is when you have a subproblem, you execute only one subproblem, right? Child function, that he calls as decrease and conquer. And all the complexities of all those decrease and conquer algorithms, as we have seen, it's not more than n, right? It is at most n. Whereas divide and conquer is at least n. We will see later that the complexities of this is at least n, minimum n onwards. It can be n log n, it can be n log squared n, so on. But what about decrease and conquer? everything was at most n, right? So either log n or log n base 3, whatever, it is still log n complexity, or n, it was never greater than n. I mean, for normal problems, you can forcefully make it greater than n, but I'm talking about natural algorithms, right? That we have seen too. Okay, now you divide this problem into many subproblems and you recursively solve them. Recursively solve this. How do you solve this problem? Again, divide this subproblem into multiple sub-problems and solve them, right? So on until you hit the base case, and in the base case, the subproblem size will be of constant size, maybe n is equal to 1 or n is equal to 2 or n is any fixed number, say n is equal to 32, right? Okay, something like that. And you solve the problem iteratively, right? And every subproblem that is greater than that base case will be solved recursively here. So once you have the solutions to subproblems, let's call them sub-solution, you combine all these solutions to subproblems, then you get the original solution, right? That's the divide and conquer technique. And there are 3 steps here. One is the divide step, where you are splitting the problem into subproblems. Second is the conquer step, right? Where you are recursively calling the subproblems. Third is the combine step, where you are combining the solutions to form the solution to the original problem. Now, look at this. What is conquer step? This is just recursion in our case, right? We just recursively call the subproblem. That's it. That's our conquer idea. There is nothing else here. It is simple. Just recursively call the subproblem. Okay, this is simple. What about divide? Divide, it depends on the problem. For many problems, we are just splitting the, say, an input array into 2 equal halves. The first half, second half, something like that, where the divide is trivial. You can do it in constant time. But in some other problems, for example, Strasson's algorithm, divide is not at all easy. It's complicated, right? For most problems, it can be easy. For there are a couple of problems or algorithms where divide step is complicated. We need to think a lot how to divide the problem. Okay, so this can take time. This can take time, right? Next, what about combine? What do you mean by combine here? For some problems, combine can be easy, right? You can do it in, say, linear time or something like that. You need to at least scan them, right? At least scan them. Or suppose they are less, maybe you join it in one shot, right? Right? Suppose there is, maybe there is an algorithm that can do it in constant time, whatever. But there are some algorithms where combine step can be complicated. Again, the best example is Strasson's divide and conquer algorithm. So there, both the divide step can be complicated, combine step can be complicated. Okay, so what is easy for you to think is divide. Typically, for many problems, we see that divide means just dividing the input array into 2 equal halves, or the number of points into, say, all points on the left x coordinate, say with x coordinate, say, less than 0 and greater than or equal to 0, something like that. For many problems, it can be simple, divide step, right? For some, it can be complicated. And combine, you might have to think a bit, right? Typically. Okay. So we will follow this template, right? This is not a standard template used anywhere in any book, but we will follow in this course, right? The way we explain the algorithm, we will follow this template for every algorithm we give here. So we follow this 6-step template. First, we give the problem. Then we give the sub-problem. And you will see why step 2 is beautiful. So sub-problem, we will encounter this idea in dynamic programming, right? So one of the most important ideas in solving the problem is thinking about the subproblem, right? So here in divide and conquer, subproblem might seem trivial to you, but you will understand the power of the concept of subproblem in dynamic programming, right? So hence we will use this, right? Step 2 is subproblem. Then step 3 is the core idea. This is where we show, okay, what is the problem? What are the multiple subproblems? How the solutions are combined to get the original solution. Step 4, we will take an example, apply this algorithm on that particular example, right? So we will show some visualizations, diagrams, or maybe step-by-step explanation, something like that for a particular example. Next, we will give the pseudocode, right? Algorithm itself, algorithm here represents pseudocode, right? And then the complexity analysis. Okay, we will follow this 6-step template. Let's start with array sum, right? You want to compute the sum of elements in a given array. You're given an array, you want to compute the sum of elements. There is one trivial algorithm, right? What is it? Scan the array, add all the elements. Okay, what is big here? This is so trivial, right? We will understand this. So we want to come up with a divide and conquer algorithm. And later we will analyze why we need it. Is there any advantage of this divide and conquer over the normal algorithm and so on, right? Okay, let's define the subproblem something like this. Sum of a subarray A of low to high. So low is one index and high is another index. Low is less than or equal to high, right? Let's define this as the subproblem, where this represents the sum of all elements in the subarray, this, right? Okay, so how many subproblems are there? I mean, if you just look at this, L is less than or equal to H. How many subproblems are there? At least here, if you don't specify.
Well, you can split it as many times as you want, right?
Correct. I mean, without looking at the algorithm, if you just look at L and H, L is less than or equal to H. So how many subarrays are there in an array?
2.
Subarrays, all possible subarrays possible in an array.
H. Because you could split, well, there's n elements and you could split each one to be one element each. So then there would be n subarrays.
Okay, so let's think about this. Suppose the elements, the indices are from 1 to n. See, 1 to 1 is a subarray, 1 to 2 is a subarray, 1 to 3 is a subarray, right?
Ah, okay.
Similarly, 2 to 2 is a subarray, 2 to 3 is a subarray, right? So how many subarrays are there?
Is it n times n plus 1 over 2?
Right. Let's say theta n squared, right? N times n plus 1 by 2. N choose 2, right? Something like this. Okay, n choose 2 number of subproblems. I mean, if we just look at this, but we will see, do we really need everything? We will see that, right? Later. Okay, fine. Now we want to compute sum of 1 to n, array 1 to n. Okay, let's see. So here is the core idea of the divide and conquer array sum, divide and conquer array sum. And see, this is like the hello world program of divide and conquer, right? Array sum, divide and conquer array sum is like the hello world program of divide and conquer. One has to really understand this problem or this algorithm before understanding any other algorithm, because all the concepts will be covered here of divide and conquer. Okay, sum of the first n elements, right? The parameter is n here, the first. So here is one example. Assume that this is arbitrary sized array, right? So here we have considered 8 sized array, but assume this is n sized array. So what are we doing here? We are step 1, split the array into 2 equal parts, right? 5 2 4 7 is here, 1 3 2 6 is here. Recursively solve the subproblem, right? Suppose you recursively solve this subproblem. So the sum of all the elements in this array is, say, 18, right? 5 plus 2 plus 4 plus 7 is 18. The sum of all the elements here in the second subarray is, say, 12. Assuming that you have recursively solved the subproblem. Recursively, this is very important to understand. Recursively solving subproblems. Okay, now you have your solutions here, right? Solution to the first subproblem, solution to the second subproblem. Now what do? You just add them. 18 plus 12 is 30. So this is the combined step, right? Step 3 is combine. Divide step was here. Conquer step was here. Third step is combine step. Combine step is constant time here. Adding the solutions, right, or answers of the two subproblems, you will get 30 as the answer. That's the array sum. So here is the core idea, right? What is the core idea? You have the entire array of 1 to n, right? Say sum of array of 1 to n. You recursively call sum of array of 1 to n by 2. So I will not show the floor, ceiling and all that, right? You can do it later. Okay, so this is sum of array of n by 2 plus 1 to n, right? When you recursively solve it, you get the, say, L sum. Left sum is this, right sum is this. You add L sum and R sum, you get the sum of the entire array that you return. And how do you solve this? Again, recursively. Split this into 2 components, right? Recursively solve those problems and combine the solution. And what is the base case? The base case is when there is only one element in the array, you return that element because that's the array sum. Simple idea, right? So here is your step 4 example, right? Proper example is like this. So you have this array, say 1 to 8. What do? What is the first step? You split 1 to 4, 5 to 8. So in this subproblem, what do? It's not an array of size 1, right? It's not the base case. You keep splitting until you hit the base case. So 1 to 2, 3 to 4, right? 5 to 6, 7 to 8. Again split 1, 2, 3, 4, 5, 6, 7, 8. You are recursively splitting. At some point, the subproblem will be of size 1. And that's the base case. If the array size is 1, you return the same element because that's the array sum, right? So it returns 5, it returns 2 here, 4, 7, so on. Now look at this. So you have L sum and you have R sum. What do? You add. You get 7. So this is the array sum of this subproblem, right? You have 4, you have 7, add. So you get 11. That is the answer to this subproblem, right? 1 plus 3 is 4. Solution to this subproblem. 2 plus 6 is 8. Solution to this subproblem. Now you have these two subproblems, right? the solutions to these two subproblems. 7 plus 11 is 18. That is the solution to this subproblem. Make sense? 4 plus 8, 12. This is the solution to this big subproblem, 5 to 8. And 18 plus 12 is 30. That's the solution to the original problem. Make sense?
So, Professor, the overall point of this is to take a problem and keep dividing it until we get an O of 1 solution to get the final answer, right? Because now each of these additions is just constant time.
Right. For array sum, it is constant time. Yes. The divide step was also constant time because it's just a split,
Right.
nothing else. Right? So divide step is constant time, combine step is constant time, no big deal, right?
Right.
But the core idea is splitting it, recursively solving the subproblems, and combining the solution. That's the core idea. Because
Yeah, okay.
this combine step and divide step, it depends on the problem at hand. Okay?
Okay, thank you.
So see, this is the example, execution of the algorithm on one particular example. Okay? So once you understand an example, right, the working of an example, I mean, you can generalize it to say 16 elements, 32 elements, and so on, right? In fact, you can solve it for any number, n. N need not be a power of 2. We used power of 2 for simplicity because it's easy to show via diagrams, right? You can evenly split. But you can use it for any n. It need not be a power of 2. Okay, so you can try it out, code it out. So here is your array sum, a of low to high. Okay, so whenever you see this, can you tell me what is the invocation? How do you invoke this function? Array sum, a of, you are invoking the function from 1 to n because that was your original array, right? So 1 goes to low, n goes to high, and you recursively solve that. This is your function invocation. The first time you call this function is like this. Function calling is like this. Okay. So let's see the function itself, algorithm, right? Array sum of a to low, a of low to high. If low is equal to high, return. This is a mistake. I should have written low, right? So return a of low. That means if there is only one element, return the same element. Done. That, right? One element is the array sum of itself. If there are 2 or more elements, then what do you do? If low is less than high, like your binary search. Remember the binary search? The only difference is, so binary search will call only one child function. But here you are calling both the child functions. So hence that is decrease and conquer. This is divide and conquer. So mid is equal to low plus high by 2. That means you split that array into 2 equal parts, right? Or almost equal. If n is not an even number, then almost equal, right? It doesn't matter. So then in parallel, you can call array sum of the left half, right? Low to mid, and array sum of the right half, mid plus 1 to high. So let's call this as L sum. Let's call this as R sum. Then return L sum plus R sum. That's it. right? See, every divide and conquer algorithm will have a base case. Base case will be, typically very simple, right? Constant size. Leave this. Now consider the recursive case. In the recursive case, so what were the three steps? Divide, conquer, combine, right? Divide is something like this. You can call this as the divide step. Divide step. Divide step. Very easy. Conquer step. Conquer is also easy. Just recursively solve the subproblems. Combine step. Combine the solutions to the subproblems. Done. Constant time. This is constant time. This is constant time. So what is the time taken for this? Right? We will see. We will analyze it. Okay. So
Professor, sorry to interrupt one more time. When you say parallel in pseudocode like this, does that when you were to if you were to implement this in actual code and you see the word parallel, does that just mean in the else statement or call a separate function?
okay, so here I made one mistake. I should have said, see, here we will learn parallel divide and conquer. Typically, all universities, right? Every book teaches you sequential divide and conquer, right? Running divide and conquer algorithms on a single computer. But here, I believe it is best to teach parallel divide and conquer because it's the same ideas, just you look at where you can parallelize it. That will also teach you how to come up with parallel algorithms, right? And you know that everything is parallel nowadays, right? Your laptops will have multiple cores, your smartphones will have multiple processors, and everything, every computer you see nowadays is parallel. But parallel algorithms is a specialized topic. I don't know why. One could easily teach it as part of divide and conquer. Hence, we will use only this parallel keyword. Okay.
I see. Okay. Okay. Thank you.
If you delete these parallel keywords from the program, you can run your this pseudocode or program anywhere, right? However, if you just parallelize this, say line 5 is parallelized, that means you are running these two function calls in parallel. I could have just deleted it. That is a serial algorithm, right? Or just adding one keyword and running these two algorithms in parallel, right, will give you a lot of speed up. But for running these kind of parallel algorithms, you will need a special compiler, a parallel compiler. Normal serial compilers will not work, right? And for example, I think GCC, right? GCC, G++ in Linux has all this capability. You need to use some special keywords they give you. So here I have used parallel. This might say something like spawn might be the keyword in this compiler, right? Intel compiler might have a different keyword. It doesn't matter, but the core idea remains the same. The core idea means you have these two function calls. If your compiler, right, supports it and has a special keyword for spawning these threads or functions, use that to call them in parallel. Okay.
Okay. Thank you.
Next, we will analyze various types of complexities. Probably we will not analyze cache complexity, right? But other types. Work. Let's define work. What is work? Work is the total number of computations. And throughout, till now, we were analyzing work. Work is the total number of computations. See, we used T of n everywhere, right? That's really the work in the world of parallel algorithms, right? So you can also consider this total number of computations as the serial running time. Running time on a serial computer, running time on a computer with one processor is same as saying total number of computations, right? So remember all the analysis we did in recursion and trees and other data structures, all those are serial running times, right? All those can be considered as work, right? Total number of computations. Here in divide and conquer, we introduce a new term called depth. What do you mean by depth? Right, this is a beautiful idea. It's in the word of parallel algorithms. What is depth? So depth is the runtime for an algorithm, runtime of an algorithm when it is executed on an infinite processor machine. Right? Suppose you have infinite processors on a machine, right? That means infinite processor just means as many processors as needed by the algorithm. That's the meaning of it. As many processors as needed by the algorithm, right? Okay, you run that algorithm. The time taken by the algorithm when you parallelize that algorithm, right, then it is called depth. When you completely parallelize the algorithm and run it on an infinite processor machine, then it is called depth, right? The time taken is called depth. Okay, now let's think about, okay, then space, you know, right? The total space consumed by this parallel algorithm, right? What is it? Cache complexity, we will not look at cache complexity. You don't need to worry about it. I just added it for extra information, right? But we will not touch it. You don't need to care for this. But know these, right? Because this is beautiful. This is anyway you need to learn, right? Space is common. This is the only extra thing. And here, this just means parallel, it's not parallel running time. Parallel running time means running time on P number of processors, on a specified number of processors. But depth is running time on infinite processors. Work is running time on one processor, right? You can combine these two ideas, work and depth, to come up with running time on P number of processors. But we will not look at all those details, okay? You don't need to worry about it. But just know how to analyze work and depth for the time, right? And space is anyway separate, okay? And let's see, how did we get this? Let's look at okay, so this pseudocode, right? The work, let's consider this as T of n. So it recursively calls this, the first subproblem n by 2, and it also calls another subproblem of size n by 2, correct? Along with it, it does some computations here. Let's call, I mean, all these computations is just theta 1. So T of n is really 2T of n by 2 plus theta 1. That's your work. That's the total number of computations. That's the runtime on a one processor machine. Okay, so analyzing time is very easy. T of n for the original problem, look at the time for the first subproblem, time for the second subproblem, time for the third subproblem, so on. Add them up. Here it is T of n by 2 plus T of n by 2. It's 2T of n by 2, done. Plus, what is the extra work you do for splitting, combining, comparing, whatever? That's theta 1. Okay. So you can generalize this as T of n is equal to time for each of the subproblems plus time for dividing, right? That is step 1, plus time for combining. Make sense? This was really step 2, right? Conquer step. Dividing is nothing but step 1. Combining is step 3 of divide and conquer. This is step 2, step 1, step 3. Okay, so here in array sum, this was equal to T of n by 2 plus T of n by 2 for conquering. Dividing is theta 1. Combining is theta 1. So theta 1 plus theta 1 is theta 1. T of n by 2 plus T of n by 2 is 2T n by 2 plus theta 1. Make sense? Simple, right? This is simple. What is complicated is depth. I mean, not really complicated here. We will see. Okay, let's call D of n. D of n, let's call D of n. The time taken to run this algorithm on infinite processor machine is equal to, let's see, so how should I write this? The meaning of this is number of parallel steps for the algorithm, right? What is the total number of parallel steps? Let's think about it. So we have divide and conquer step, right? So parallel steps for dividing plus combining plus conquering. So this was step 1, this was step 3, right? This was step 2. Dividing anyway, we have to do this. You cannot parallelize this, right? Okay, so let's call it as, see, if we don't have parallel, we are not parallelizing it. So theta 1, combining theta 1, conquering. Let's think about conquering. There are 2 function calls. We are running them in parallel. So it's like this. There are 2 function calls. You're running them in parallel. So the time taken for completing this task, because you're running them in parallel, right? And depth is related to the parallel time on infinite processor machines. That means it is as if you're running only one task. It does not matter whether you are running 10 tasks or 100 tasks in parallel of the same subproblem. This is also n by 2. This is also of size n by 2, n by 2, n by 2, n by 2, right? The parallel running time here is theta, or you can just say T of n by 2, just one T of n by 2, right? Because whether you run one subproblem or 2 subproblems, 3 subproblems in parallel, it does not matter. The parallel running time won't change. Does this make sense?
Yes.
Right? So here you are only concerned in this parallel running time, the depth. Okay, so d of n by, oh, why did I write t? It's d, depth of n by 2, depth of n by 2. D of n is equal to theta of 1 plus d of n by 2. When you solve it, you get log n. That's why you have d of n is equal to d of n by 2 plus 1. It's log n. Space, anyway, you need to use space for both because you're running them in parallel, and you have to use space to solve those problems. So it's theta n, total space. Total space is theta n. Right? You cannot do better than theta n. Right? So, okay. Now let's think about it. See, another idea is this. See, if you look at what is the meaning of work, what is the meaning of depth? The work is the total number of nodes in this graph, right? And depth is the height of this graph. Can you tell me what is this total? What is the total number of nodes here? If the array is of size n, what is the total number of nodes?
And
Is it n? This is n, right? So, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. Right, probably we have 8 more here, say around 32 or something like that. So what is the total number of nodes here? It is theta n. Total number of nodes is theta. See, this is anyway n, right? This is n. What is this? N by 2 plus n by 4, n by 8, so on up to 1. What about this? N by 2, n by 4, n by 8, so on up to 1. So you know this sum is anyway n, this sum is anyway n, right? So 3n or whatever, verify this, right? It's constant times n. Hence, the work is n here. What is the depth? Height. What is the height of this graph? This is really a DAG, right? A directed acyclic graph. So what is the height of this? Height. What is the height? It's log n here, 2 log n. So theta log n. Make sense? So got the idea behind what is work and what is depth? Work is the total number of computations. So each node you're computing, you're dividing, splitting, combining, and all that, right? So work is happening everywhere. Computation is happening everywhere. What about depth? Depth, you don't care for how many tasks are run in parallel. This will be considered as one parallel step. This will be considered as another parallel step. This will be considered as third parallel step, fourth parallel step, right? Fifth, sixth, seventh. So here, what is log 8 is equal to probably 4, right? No, sorry, 3. 2 times 3 is 6. So though you see that the number is 7, it's not theta n, it's 2 times log n here. Okay, so you need to analyze the height as a function of n, as a function of n. Here it is log. Got the meaning of and the differences between work and depth, right? With that, let's move to another problem. Suppose you are given a map, right? A closed function in a 2D plane, a closed shape. I mean, you can generalize it to, other dimensions also, but let's consider 2D shapes, a closed shape. Defined by some function f of x, maybe something like this. You want to find the area of this closed shape. It can be some arbitrary closed shape, right? But you're given the function of this, right? Function of the perimeter, and you want to find the area of this. How do you even find it? We can find the area of rectangle, triangles, and many other simple shapes, right? But arbitrary closed shape, how do you find it? Right? So there is a beautiful idea here. This uses again randomizations. So this is not 100% correct result, but approximate result. So we get an approximate answer using randomization. You can also call it an approximation algorithm, right? Using randomization. So, I mean, we will define the ideas and all later, but let's look at the subproblem. Hits of K, the number of points falling inside the closed shape with K attempts. And we want to find hits of N. Okay, just remember this. We will come to this later. So what is the idea? The idea we will follow is this. The core idea is this. Suppose the shape is given like this, shaded, right, in blue. What we do is we create or we come up with some random points. We create as many random points as possible, generate as many random points as possible, and check whether random points only in this closed shape. Look at this, in this rectangle. See, in this rectangle or square. This rectangle should cover this closed shape, and we can always find it. Why? Because, think about what is the y max here and y min here, right? X max here and X min here. You can always create a bounded rectangle like this, or you can also create any rectangle that encloses this closed shape. Anything works, right? But make sure the closed shape is completely covered in this rectangle. Now what you do is this. You generate a lot of random points in this rectangle. That random point, each point, might be inside the shape, or it might be outside the shape, but inside the rectangle. It will always be inside the rectangle because you're generating random points inside the rectangle. But two things can happen. That point can be inside the closed shape. It might be outside the closed shape. If you find a point that is inside the closed shape, you count, right? You increment your count. Now, suppose you had n points, right? You generated n random points in the rectangle, and suppose the number of points that were inside this closed shape was, say, hits, right? H or hits, whatever. So this is called a hit. If a point is inside a closed shape, it is called a hit. And suppose you have an algorithm to check whether a random point is inside a shape or not. Okay, there are algorithms for it, right? Given a point, and given a shape, you want to check whether that point P is inside the shape or not, right? Inside. Suppose you have access to this function, is inside P shape. There are algorithms, okay? We will make use of these algorithms. Then you know that it is a hit. If the point is outside the closed shape, it is a miss, right? Count the number of points that are inside the closed shape divided by the total number of points, that is approximately equal to area of closed shape divided by area of rectangle, right? You know the area of rectangle, it's easy to compute, width into breadth, right? Length into breadth, whatever. Simple formula. You know n, you know the number of points that went inside the closed shape. So what is the area of the closed shape? It is hits divided by n times area of rectangle. Done. Beautiful idea, right? See, that is the idea we will use. Okay, so suppose hits of n divide the number of points n by 2. Suppose the number of hits is 7, 6, you add them. So we will see the pseudocode and it will be clear. So here is the pseudocode. you are given f of x, right? F of x gives you the closed shape, right? You find the x minimum, x maximum, y minimum, y maximum, right? Simple idea is to create a bounding rectangle, something like this. Bounding rectangle. And you can always find this easily, right? X min, x max, y min, y max of the functions. Okay. Extremes of this function. So once you have this, you can find the area of this rectangle defined by this. See, what is this? This is y min, this is y max, this is x min, this is x max. So what is the area of the rectangle? X max minus x min times y max minus y min. Hits is equal to 0. Okay. Now what you do is you try n points. You generate n points, n random points inside the bounding box. And you need not generate these points in a serial order. Why? You can always use a parallel algorithm, right? In parallel for I is equal to 1 to n, right? See, all these n points can be created in parallel. Okay, so find a random point. Let's call it as x comma y. If x comma y is inside the shape, the region, right, f of x, then increment your hits. Okay, increment your hits. If x comma y is outside the region, you don't need to worry. You don't need to increment the hits. That's it, right? So at the end, you will have the total hits, right? So you will have the total hits. Now do hits divided by n times box area. That gives you the approximate area of the region. That's the algorithm. Okay. Now think about it. We know how the algorithm works, but we have a parallel for here. Previous time we called two functions in parallel. Now we are multiple iterations. We are running these multiple iterations in parallel. So where is this divide and conquer coming from? See, you can spawn a loop. You can parallelize a loop. I mean, not all loops, but many of the loops. Okay, so here they are independent, right? Random number generation has nothing to do with dependency. So you can generate n random points in parallel. They are independent, right? And you can also check them whether it is inside the region or not in parallel. Hence, we can run a parallel loop. But where is divide and conquer? Okay, so whenever you use parallel for loop, right, in a parallel program, the way the compiler solves this problem is something like this. See? So it is like this. Internally, you can assume it solves the problem like this. Hits is equal to hits of n. Now you have this hits of n, right? That function, that's a recursive divide and conquer function. So what is the idea here? Hits of, you call hits of n by 2. N by 2. Hits of n by 2. Because you just want to generate n random points, right? In parallel, the way it is implemented in the compiler will be like this. A recursive call like this, and again split it such that so n is equal to 1 point. This is the base case. All n points will be here. See, all these are the n points. Now In the base case, what happens? You find a random point. If it is inside, you return 1, else you return 0. And then you combine, right? See, this might be a hit, this might be a miss, right? Then you return. When you return, you add the hits from the first call and the second call. So this is total hits is 1. So this might be a hit, this might be a hit. Return, add them. This might be a miss, add them. Miss, hit, add them, right? So here, so hits from the first function, hits from the second function, 3 here. So this is 1. So totally 4 hits. Right? Something like this. 4 divided by total number of points may be n times bounding box area. That should give you, oh, say 8 here. Right? That will give you the area of the closed shape. Make sense? So even if you use a parallel for loop, that is very famous, right? In almost all parallel programs, you will see parallel for loop. So how do you think about this? 1 to n plus c of 1 to n. You are adding 2 arrays, right? B1 to C1, B2 and C2, so on. And you are assigning them to A of 1 to n. You don't need to do it serially, right? You can run it in parallel. So you can just use parallel for, right? I is equal to 1 to n, and then do all these adding, assignments and everything. Now, what we learned from this example is that every parallel for is really a divide and conquer algorithm. It's a parallel divide and conquer algorithm, isn't it? Every parallel for loop is a parallel divide and conquer algorithm. And we know the divide and conquer algorithm from array sum. So the same idea applies to every parallel for loop, right? Among, infinite number of algorithms. Okay. So whenever you see a parallel for loop, or if you think of for loop or any loop can be parallelized, internally you have to use a divide and conquer algorithm. Else there is no meaning to this parallel for loop, right? The way it is implemented is using a parallel divide and conquer. So this is a powerful example, right? Okay, what is the complexity? Exactly like your array sum. If you understand the complexities of array sum, this is cakewalk. Same. It's 100% same. No difference. Okay, let's move to prefix sum. Oh, before looking at it, so what I can do is let's cover recurrences first, and then we will touch prefix. Right? Okay, let's start with recurrences. We completed 2 problems. We went in depth into those, right? And we saw recurrences everywhere. See, work complexity is a recurrence, depth complexity is a recurrence, space complexity is a recurrence, cache complexity is a recurrence, right? So almost everything is a recurrence here. What about decrease and conquer? We saw recurrences there also. So decrease and conquer and divide and conquer, all the complexity analysis will be done using recurrences. So should we solve each and every recurrence, right, manually deriving all these formulas, or is there one theorem that can attack any recurrence in one shot so that we can quickly know the complexity in one shot, right? So let's understand something about recurrences and see a theorem, a very important theorem. So we will cover 4 different methods, majorly 3, but one is I mean, one is also a method, but it's a dangerous method. So we will see 4 different methods. So one way to solve a recurrence is this: iteration and substitution. For simplicity, assume that the base case is always t of n is equal to 1. I mean, the t of 1 is equal to 1, right? When n is equal to 1, the time taken is 1 or constant, something like that, okay, for simplicity. Now let's see how to solve the recurrence if our recurrence is something like this: t of n is equal to t of n by 2 plus 1 using iteration and substitution. Substitution, that means substitute iteratively, iteration, right? Substitute the value in iterations. That's the meaning of this. So t of n by 2, what is t of n by 2? T of n by 2 is t of n by 2 divided by 2, right, plus 1. But n by 2 divided by 2 is n by 2 squared plus 1, right? So now again substitute the value of t of n by 2 squared. It is t of n by 2 cube plus 1, right? So keep doing it for k iterations. The first iteration, this is the second iteration, third iteration. Keep doing this for k iterations. After k iterations, what do you get? T of n by 2 power k. Look at this. The problem size is decreasing by a factor of 2, right? 2 squared, 2 cube, right? 2 power k. And the number of ones here will be k ones. Okay, so now this can be replaced with k, right? So t of n by 2 power k plus k. Now what do? You know the base case, right? It has to hit the base case. Every subproblem, if you keep on dividing it, it has to hit the base case. Okay, that means n by 2 power k at some point in time will hit the base case. So substitute n by 2 power k is equal to the base case. This means n is equal to 2 power k, which implies k is equal to log n base 2, right? So wherever you have n by 2 power k, substitute 1. Wherever you have 2 power k, substitute n. Wherever you have k, substitute log n base 2. So n by 2 power k, replace it with 1. You have k, replace it with log n base 2, right? If you had some 2 power k somewhere, replace it with n. See, you don't want terms in terms like k, right? Finally, you want the final answer in terms of n only, because n was your input parameter. So t of 1 plus log n, t of 1 is 1 as we already assumed. So it's theta log n complexity, right? A simple example to show iteration and substitution. But you can complicate this. You can complicate this. Suppose you have a recurrence like this: 2t of n by 3 plus theta n. So what is the meaning of this? Maybe there is a divide and conquer algorithm, right? Maybe something like this: t of n by 3, t of n by 3, right? Plus theta n. So that means, look at this. Let's analyze this. It's a divide and conquer algorithm where there are 2 child functions, 2 times t of n by 3, right? 2 child functions, and each child function takes time t of n by 3. That means the problem size is decreasing by a factor of 3. n to n by 3, n to n by 3 here also. The problem size is decreasing by a factor of 3. There are 2 subproblems. When you solve them both, you get 2t of n by 3. And probably for dividing the problem or combining the solutions, you need linear amount of work. So theta n. That's the meaning of this, right? Okay, let's proceed. So T of n is less than or equal to 2T of n by 3 plus Cn. Instead of theta, we replaced it with some upper bounded by some constant, right? That's the meaning of theta. I mean, we should also show lower bound. Ideally, we should also show lower bound. That means we should also have an equation something like this, greater than or equal to 2T of n by 3 plus say C dash n, right? Because this is both upper bound and lower bound. But here we will just focus on this upper bound, okay? Now, T of n is less than or equal to 2T of n by 3 plus Cn. Substitute, what is this? T of n by 3 is 2T of n by 3 squared plus C n by 3, because the problem size is n by 3. So C times n by 3, this is n by 3 divided by 3. So n by 3 squared. Again, simplify this, 2 squared T of n by 3 squared plus dot dot dot. What is T of n by 3 squared? Expand it. See, what some students do is they just expand it for 1 or 2 iterations and they write the pattern. No. Right? With 1 or 2 iterations, you will not see the pattern. And even if you think you see a pattern, it might be an incorrect pattern. Right? What is an example? See, let's think about it. If I give you just these 2 numbers, can you predict what is the next number? You can say you're adding 1 everywhere. Maybe it is 3. Maybe it is 3. Maybe it is not. Maybe it is this, because you are multiplying by a factor of 2 every time. So here you are adding, right? So if you predict that the next number is 3, and if you generalize it to k, it need not be. Maybe the general formula might be something like this, 2 power k minus 1 or something like this, right? So you need to expand it, substitute and expand it for 3 or 4 iterations. Only when you are 100% sure of the pattern, then generalize it for k. So here we have showed the substitution and iteration for 3 steps at least, right? N by 3 cube. See, now you clearly see a pattern. You can take Cn out. And what is this? This is a geometric series, right? Okay, so generalizing it, you get something like this. 2 power k T of n by 3 power k plus Cn and a geometric series. A decreasing geometric series, you don't need to worry. It's always a constant, right? 1 plus r plus r squared plus r cubed, so on up to infinity. Even if it goes to infinity, if r value is in the range 0 to 1, then this is a decreasing geometric series. You don't need to worry. It's constant, right? It's constant. So this is really, it remains the same. Okay, I mean constant times this, so C dash, we have used C dash here. Okay, so the asymptotics won't change. So what about this? 2 power k T of n by 3 power k. So here we consider n by 3 power k is equal to 1. That's the base case. That means 3 power k is equal to n, or 2 power k is equal to, or k is equal to log n base 3. I mean, there can be multiple terms, right? You should be able to derive everything from this. So why do we care for 2 power k? Because 2 power k is required here. See, another idea you could have used is something like this. 2 power, what is k? K is log n base 3. So you could have just used something like this and then change it to this, right? So any idea that works is fine. Okay, so like when you substitute, 2 power k becomes this. T of 1 is constant. C dash n remains the same. Now, what about n power log 2 base 3? You know that log 2 base 3 is less than 1. Correct? This is less than 1. So if this is less than 1, n power less than 1, what is it? Does not dominate. So because you have n here, so O of n. See, this is why we required all that asymptotic analysis, right? You want to compare two functions and simplify, so on. Majorly for analysis of algorithms, we want to compare two functions, see which one is dominating, which one is not, so that we can analyze the final complexity of programs, algorithms. Okay, so this is method 1. What is method 2? Recursion tree. So here is our recursion tree. 2t of n by 3 plus cn. Now look at this. T of n by 3, t of n by 3. Because there are two child functions, each child function is of size n by 3. Again, t of n by 3 squared, t of n by 3 squared. Keep dividing. So this is like a decision tree. This is our binary tree, right? You can also consider that as a, what was the name we gave? Is it a perfect tree or something like that? Perfect tree. Perfect tree. Right? Okay, what happens? In the base case, this is really 1. T of 1 is 1. T of 1 is 1. Now, okay, so this is about the conquer step. What about the divide and combine step? It is Cn. So whenever you are dividing it, splitting it and combining the solutions, the step 1 and step 3, right? Divide step and combine step are taking Cn time. So the divide step and combine step in level 2 is taking this much time. Why? So that extra time, or so time here it is Cn by 3 for this, Cn by 3 for this. When you add both of these, you get 2 by 3 Cn. Right? So similarly, for each, the extra component is Cn divided by 3 squared. But because there are 4 such subproblems, you have 4 by 3 squared Cn. That is 2 by 3 whole squared Cn. Right? Okay. Now look at this. I need to... How many ones are there here? 2 power log n base 3. How did we get this number? This is a binary tree, right? The branch factor is 2. Everywhere, the branch factor is 2. So it should be a power of 2. You know that it should be a power of 2. 2 power what? 2 power height of the tree. What is the height of the tree? Log n base, this is decreased by a constant factor, right? What is that factor? 3. So the height of the tree is log n base 3. So 2 power log n base 3 are the total number of leaf nodes. And each leaf node does constant work or amount of computations. So total time required in the for all the leaf nodes is 2 power log n base 3 or n power log 2 base 3. That is less than n. Less than n. This is less than n. Right? Less than n. So the point is this. Every divide and conquer algorithm, there are a couple of computations in the base cases. All these are the base cases. And all these are for dividing and combining the tasks. So the total amount of computations is, if you add all these up, it's C dash n, right? Theta n. But if you add all the base cases work, it's less than n. So which one dominates? N dominates. That's it. So this is the recursion tree approach. Okay. So this is the recursion tree approach. I will skip method 3, unimportant. Method 4, master theorem. So see, you need to understand master theorem. This is like the deathbed theorem, right? What is the deathbed theorem? Even on your deathbed, you need to remember the master theorem. Okay, so what is this theorem? This theorem is so beautiful that given a recurrence, you can directly predict the complexity of the recurrence that has that, complexity of the algorithm that has that recurrence. It's a beautiful result. You don't need to do all that substitution, iteration, recursion trees, whatever, right? It's just in one shot. You have a couple of cases, check which of the cases work, and get the complexity of that algorithm in one shot, right? That's the beauty of this master theorem. Okay, let's understand this master theorem. So suppose our recurrence is something like this. T of n, you have the base case. The base case is if n less than d, then it is C. If n is greater than or equal to d, then it is a t of n by b plus f of n. Now let's understand this. D is greater than or equal to 1, it's a natural number. It's a fixed number. So, I mean, you don't need to worry about it a lot because we are not using D anywhere here. Assume that it's a fixed natural number greater than 1, right? Doesn't matter because it does not come in the formulas here. Next, C. What about C? C is some constant again. It can be 2, 3, it doesn't matter. Who cares, right? C does not come here in the formulas. So you don't need to worry about C, D. Let's focus on A, B, and f of n. Very important, super important. Okay, let me move here. A, look at the constraints. A should be greater than or equal to 1. These can be real numbers. And C, okay, leave C. C should be a constant. And B is greater than 1. That's a real constant. And f of n is a positive function for n greater than or equal to d. And we analyze these positive functions in the first class itself, right? We are assuming positive functions. We are never assuming negative functions. Okay, let's focus on A and B. A is greater than or equal to 1. So it can be 1. If it is 1, there is only one subproblem. It also covers decrease and conquer algorithms, isn't it? If A is 1, that's a decrease and conquer algorithm. So this theorem works also for decrease and conquer, for divide and conquer as well. Okay, A greater than, what if A is greater, A is equal to 2, A is equal to 3 for array sum, everything, it works. Good. A can be, say, 1.6. A can be pi. And do not worry about what do you mean by how can you have pi number of child functions. Of course, we cannot have, but the point they are trying to say is at least the formula works even if A is any real number greater than or equal to 1. It need not be an integer, right? Okay, next, T of n by B. What is B? Can B be 1? No. If B is 1, what happens? Tn calls Tn. Doesn't make sense, right? Tn calls Tn. That means it goes into infinite recursion mode, right? You cannot solve the problem. We saw a similar problem in the exam, I believe, right? But not a recursive. Yeah, it's a recursive function, something like this, but there were kind of two functions. So b should be greater than 1. I mean, b can be 1.0003. b can be any 1 plus epsilon, epsilon greater than 0. b can be 1 trillion, whatever, right? It can be any real constant. It need not be a natural number always, right? Any real, but make sure it is greater than 1. Okay, what about f of n? F of n is positive for n greater than or equal to. Then the complexity is something like this. First, find delta. What is delta? Delta is log a base b. You know what is a, you know what is b. So delta is log a base b. First find that out. Then you have three cases. If f of n is O of n power delta minus epsilon for any positive epsilon, any positive real epsilon, right? Then the complexity is theta n power delta. If f of n is theta of n power delta times log power k n. So here k is a natural number, right? K can be 1, 2, 3, 4. We might see some examples later. Okay, then it is f of n log n. T of n is f of n times log n. The third case, this is the third case. What is the third case? The third case is if f of n is at least, right? This is at most, this is exactly same theta, this is at least n power delta plus epsilon. That means if f of n is asymptotically greater than n power delta, right? If f of n is asymptotically greater than n power delta, then of course f of n should be the winner, right? F of n should be the winner. And f of n must also satisfy one constraint, that f of n must be greater than a times f of n by b, right? We will see this constraint later. But the point is this: if f of n is asymptotically greater than n power delta, then f of n is the winner. If n power delta is asymptotically greater than f of n, then n power delta is the winner, right? But if both are asymptotically similar complexities, why do I say similar complexities? Both have n power delta as the power, but okay, so we will see some examples later. Assume that if both have similar complexities, then, right, then you just multiply by a log n term, right? You just multiply by a log n term, right? So that's about the theorem, and we will see all this explanation in the next session, right? But go over this, we will see all this explanation in the next session. So we will stop here. So any questions, team?